All right, everyone, thank you for coming back. We've got great attendance. Welcome to the second session of the WebAssembly workshop. I'm very happy to announce our second keynote speaker, Oscar Spencer, who's going to be talking about Wasm GC and the future of high-level language compilation. Please take it away, Oscar.
Absolutely. So thank you, everyone. My name is Oscar Spencer. I'm a co-author of the Grand Programming Language. I also am on the technical steering committee for the Bytecode Alliance, but that's not really relevant for this talk. And yeah, I'm going to talk about Wasm GC. So first, let's talk a little bit about garbage collection. So low-level languages like C require users to manually free allocated memory, so you as the user of the garbage collector. High-level languages add code to your program that automatically free objects when they're no longer used, and that's the garbage collector. Garbage collectors are often very large and complicated, which can affect WebAssembly modules adversely. So if you're a low-level language like C, this isn't really a big deal. Your Wasm module, only a very small % of that module is code for, say, malloc and free, right? Very little code that affects your Wasm module. But if you're a high-level garbage collected language, this isn't ideal because you've got a whole garbage collector that you're shipping with every single WebAssembly module. And that's not fun. We want to have our WebAssembly modules be nice and small, right? So before WebAssembly GC, the way that garbage collection has worked has been that the runtime hands you a chunk of linear memory and says, hey, have at it, do whatever you want. So if you want to throw a garbage collector in there, go for it. If you're going to do something else, that's completely up to you. But browser engines already have world-class high-performance GCs. So there's generally no reason for compiler toolchains to have to include a full garbage collector into every single WebAssembly module. Granted, if you want your garbage collector to do something ultra fancy that isn't supported by the runtimes, that's a different story. But for the most part, you can get away with just using the garbage collector implementation that's already in the place where your WebAssembly module is going to run. So goals of the Wasm GC proposal, provide a way for Wasm modules to utilize a runtime's garbage collection implementation and make sure it's generic enough to work for any language. So this is the dream. We have a WebAssembly module where there's no memory management code whatsoever. All of the code in your WebAssembly module is just your user code. That's the absolute dream. So what does this actually mean in practice? Well, you can make structs and arrays. That's what the GC proposal is. So a lot of folks get really worried when they hear about the GC proposal. It's like, oh, WebAssembly has this whole GC thing that I have to worry about now. All it is you can make structs and arrays, and then ideally, maybe, possibly, they'll be freed at some point. That's the idea. It's really simple. If you look at this WebAssembly code here, we create a new struct. It's got some values in it. We create an array. That's it. It's really not too scary. That's everything that has to do with Wasm GC. So the important thing to note here is that the proposal does not prescribe how garbage collection happens. So the runtime itself, or the runtime that you choose to use, can decide what method of GC is going to happen. So let's say you've got really short-lived executions. Maybe you have something that's just a function that's going to execute one time, and that's it. Do we really need to do GC? Probably not. In fact, my favorite GC implementation is exit. It works really, really well. I highly recommend if you've never tried it. But if you've got a real-time application, something that's really intense, it needs to run continuously, maybe you want to have something like a reference counting algorithm, where it's like you amortize all the garbage collecting over the course of your program, so you make sure that, okay, this is always going to run very consistently. Versus if you want something to be really high performance and you don't mind pauses, you can have a massive mark and sweep GC, that's fine. But this is completely up to the runtime that you run in, right? This is not you doing something to your WebAssembly module to change how that works. And so that's a big deal. Your WebAssembly modules and any compiled dependencies that are in there don't need to change for the type of environment that your code is going to run in. And so that's a big deal for portability with WebAssembly, right? So we get a bunch of new reference types. So we have func refs, so you can explicitly reference a function, external refs for values that are outside of the WebAssembly VM. And then we've got this nice, beautiful type hierarchy of any refs. Underneath those EQ refs, those are references that you can check if the two references are the same. I31s, which Those are for your unbox scalars. You lose a bit, so the runtime can use that to say, okay, this is a value that's on the stack and not a pointer. Structs and arrays, which we mentioned before. You get field types. So your field types for your structs and arrays can be any of the core number types, I3264s, F3264s, or any reference type. Fields can have a special pack type, so they can be packed I8s or I16s, and fields, of course, can also be mutable. We also get a wonderful subtyping system where you can declare your struct and array types as open, and that allows them to be subtyped later. So this is a big deal. One thing that I'll note here is that the way the subtyping system works, if you have an array is a subtype of another array. If its field type is a subtype of the other field, and for structs, it's the first in fields of that. This actually is really elegant, in my opinion, for how this works, but we'll talk about that a little bit more later. We get a bunch of new struct instructions, so struct new and new default, so you can create a struct with values, or you can create one with just default values. Get, signed, and unsigned, set, same deal for arrays, but we also get these beautiful new data, new elem. So if you have data segments or element segments, you can initialize from those. Additionally, arrays keep track of their lengths for you. So if you're a compiler author and you are used to storing your array length somewhere, you don't have to do that anymore. You can just ask the runtime for it, which I like that. It makes me happy. For those unbox scalars, you have ref I31 to create those I31 values, and then you can get the value back either sign extending or not. Casting. This is where things get a little bit more fun. So ref test, you can test whether reference is of a certain type. The cast instruction, you can cast both up and down, so you can lose specificity or you can gain specificity. You will incur some runtime costs for doing that, but maybe that's okay. And then you can do branch on cast and cast fail for if you're trying to get real dynamic and have a bunch of fun there. And of course, we have that ref EQ instruction to test equality for references that are EQ types. I want to talk about some of the quirks of Wasm GC. So non-nullable locals. If you're writing a compiler, this is something that you might run into, that I ran into, that I thought was kind of annoying. But locals are only evaluated in their current block context. So what this means is, if you look at this function on line 3, we have this local that's a struct, and that struct, it's not a mutable local, right? We're just going to keep the value in there. In this block, we initialize that local with this struct value. And then outside that block, we try and get the value of that struct. And this is a validation error. Why is this a validation error? Because it would be horribly complicated for the validator to test whether or not all your locals are actually initialized everywhere. So this is a restriction. That is okay. I'm fine with this restriction. But depending on the way your compiler is set up, you might have to do some refactoring to deal with this. But that's okay. The next is mutability. So it's possible to create immutable recursive types, but it's impossible to create values of those types. That's partially because immutable types are not subtypes of mutable types. I brought this up, and Andreas was like, just because your language has these immutable structures doesn't mean the implementation has to be immutable. But Andreas, I say this. I want it. And but there are actual real reasons why you might want something like this. The first thing I think about is optimizations. It's very easy for your optimizer to see, oh, this object, it's immutable, it doesn't get used, it's never getting mutated, we can throw it away and do optimizations like that. But if you think about things like the component model, which we'll also talk a little bit about, I might want to pass a reference to a struct or an array from one component to another. And in the component model, I can do this without a copy because it is semantically correct all the time if it's immutable, and maybe some of the time if it's mutable if you're able to prove a couple things about it. But this is actually a big deal. So this is something that's being discussed, something that might actually happen. And the last quirk that I'm going to mention here is arrays of mute I8s. So if you're not using linear memory at all anymore, and you want to have an array of just data, of just bytes, We don't have efficient ways to load or store 16, 32, or 64-bit values with this. If you want to deal with a bunch of 64-bit values, you could just use a 64-bit type. But if it's just bytes and you want to get one value out, then it's annoying in the other way. This is not something that I'm worried about. Everyone who sees this says, yeah, we can add that. That's fine. So that also makes me happy. Let's talk about Grain. Grain today, it's linear 32-bit memory. GC is performed via reference counting, and we only leak memory sometimes. Yeah. That's the dream, right? But some of the major considerations here is Grain has fully generic first-class functions. So we want to do things like list.map, and we want to compile that thing one time. We don't do monomorphization or anything like that. We want a truly generic map function. So to do that, we have to have a uniform data representation. This is what compiling an apply function, so a function that takes a function f and a value x and applies f to x. This is what this compiles in the linear memory version. So if you look on line 2, we have 3 parameters. We have 3 I32s. The first one, that's closure argument. Don't worry about that. The second 2, they're I32s, which, yes, I said any value, but we have to have a uniform data representation to represent this properly in Grain. We chose I32s for that. Decref, that's a part of our reference counting, but we do a call indirect. So we pull the pointer to the function in the function table from the closure, and we do a call indirect on it. That's how that gets compiled right now. So we got to do something. We can't use I32s anymore. That's not going to work. So what are we going to do instead? We're going to use any refs for everything. So that's fine. It can be anything. Well, what's wrong with that? Which, that's a little bit sad if you think about it, because Wasm GC gives us all these rich types for heap values. But if we actually use those types in the type signatures, then we'll get the same issues as if we try to use values other than I32. But that's OK. With some fun compiler optimizations, there's lots of times where we can just use those values and avoid a bunch of casting and things like that. But on that note, ref casting everywhere sucks. It's awful. I hate it. But it's a necessary evil, which most of the time the optimizer can actually figure out that some of the types are the same and can actually get rid of a bunch of these casts, which are pretty great. And that's the same thing when it comes to the actual runtimes as well. This is what that apply function looks like with Wasm GC for us. So on line 3, if you look at those parameters, there were I32s before. Now they're any refs, which is great. Now instead of doing a call indirect, it's a call ref. We no longer have the function pointers in function tables. Now we have just actual function references, and we can call those references that exist in closures, and that makes me very, very happy. And you see we've got these 2 ref casts here. So one is a cast to the closure type, so we can say this is our actual closure type. That one I'm pretty sure we can get rid of from the compiler. That's just, I just need to go heads down and get rid of that one. But this one down here is actually calling the function. We do have to do the ref cast here to guarantee to the type checker, yes, we are going to call a function of, in this case, it's 3 arguments because of the closure argument, but otherwise we are going to be able to call that function with those arguments. So that's actually not too bad. That's not too different than this right here. Second major consideration. Grain supports generic structural equality. So we want to be able to have one equality function that can compare a list of things, compare strings, compare numbers and whatnot, which to do this, we need to be able to walk our data structures, which in linear memory, that's actually fairly easy to do. They're just bytes in memory. You do whatever you like. You can have one function that walks all of them. You can't walk your data structures in Wasm GC. We don't have a way to do that. We don't have any fun reflection-y type things that let you say, hey, how many fields does this struct have, or something like that. We don't have anything like that. And I think that's OK. I think there's a fine limitation. I think we're going to keep that. But this does mean that now we have to do some new things like creating special walker functions for each of our types, which that can maybe bloat code size a little, but it's not something that I'm really worried about. So I don't think it's too big of a deal. But maybe in the future, we might get some fun reflection-y type things. Maybe. Maybe. All right. Major consideration number 3 is that Wasm the component model, as we heard earlier, only work with linear memory. But we don't want to lose support for them in Grain because people seem to like that quite a bit. But the fun thing there is that nothing's stopping you from using that linear memory anyway while you have GC instructions. So you can just copy into linear memory when you have to talk to WASI, or in the case of the component model, copy into linear memory to conform to the canonical ABI. What I will say about this, though, is that folks are actively working on implementing the canonical ABI for Wasm GC, so you won't have to do those copies anymore. And then, like I mentioned earlier, potentially you can copy things across the component model boundary without actually doing a copy at all. You can actually just say, hey, here's a pointer to that object, and it's perfectly fine. So potentially, the component model could be even better with Wasm GC than it is with the linear memory version. And let's talk about some of the compilation effects here. So on binary size, an empty grain program reduced in size from 3K to about 300 bytes. We put metadata and other runtime stuff in every single program. The optimizer can't prove that for an empty program it doesn't need to do all these mutations in linear memory. But with Wasm GC, the optimizer can prove that. It can say, oh, I see you allocated these objects and you don't actually do anything, so I can just get rid of them. So that's phenomenal. That made me very happy. Could I have written a better compiler? Yes, but I'm happy the optimizer did it for me. For a Hello World program, we saw a 34% size reduction on that. So that is, we don't have our reference counting implementation in the module anymore. So it's a lot smaller. That's awesome. And then talking about performance, for list allocations, something that's pretty important to us. In Wasm time, the GC version is a tad slower than linear memory. The GC implementation of Wasm time is fairly new. It's only going to get better as it gets more mature. So not worried about that, but performance is pretty neck and neck, so fine. In the Wasm Edge interpreter, the GC version was way faster than the linear memory version. And that kind of makes sense if you think about it, because you're not emulating as many of the just do this thing in memory. So that kind of makes sense. And for something like V8, yeah, turns out they really know how to allocate them objects, baby. Yeah, it screams in V8. And that makes me super happy. For Bigint math, we see pretty much the same thing. One thing that you'll notice here is that for the V8 side, there is no bar. That's not because it didn't work. I thought it didn't work when I ran the benchmark because it finished instantly. And it took me a while to track down what was actually going on here. And it turned out that V8 said, well, actually, we don't need to do any allocations for this whatsoever. You're just doing some math, and we can just optimize all that away and just do the math. And so it's dumb fast in V8. So that's some of the nice things. You get so much more semantic meaning out of allocating objects than you do just writing bytes to memory randomly. So to recap, Wasm GC makes the implementation of your high-level languages a lot easier. Just create some objects. Nice. Makes your binaries a lot smaller. The fact that your runtime can choose how garbage collection happens is a huge game changer. And the more high-level language that we're able to bring to WebAssembly, because we have GC, just makes the WebAssembly ecosystem that much better. And with the component model, I know folks don't like thinking about it, but we have Python and things like that running in WebAssembly. That's actually a really big deal for us. So the fact that Wasm GC is enabling all this is absolutely phenomenal. And with that, thank you very much. Appreciate your time.
Thanks a lot. So we have a good amount of time for questions. We just go up to the mic.
I'm curious if you have subtyping on function types in Grain and whether that was an issue for mapping to Wasm GC?
We don't. So that wasn't an issue for us. I would imagine that it would probably be fine depending on what kind of subtyping you had for your functions. You're just going to have a bunch of casting, which is OK. I don't think it's too much of a big deal. But if you are trying to do something super dynamic, that you could run into a big cost by having to cast that much.
I'll just mention, so Virgil does, and it is an issue for us.
Oh, OK.
Hello, this is a bit of a dumb question, but so you mentioned structs are subtyped by extension at the end, correct?
Yes. Well, you have to. Your first in fields have to be subtypes.
Yeah. So
but then you can add more.
Okay. Yeah. And then second thing is, okay, so let's say I have a struct field in a struct, or more interestingly, a struct field in an array. I can mark that as final, and then is the compiler generally smart enough to do, for example, like array of structures rather than array of pointers?
Depends on your compiler.
Okay.
Yeah, but so the dream is to have your compilers be able to be smart enough to do optimizations like that.
Okay, yeah. Well, I guess actually...
I don't know if anyone's doing that today.
Yeah, I suppose it might break things if I take a ref to the structure, but I'll stop talking now.
Hey, so thanks for the very friendly presentation of the GC proposal. Well, actually, we shouldn't say proposal anymore.
Yeah, I guess it's done now.
It's done, right? Like, I had one comment, I guess. So one thing you said is that for real time, it's nice that you can switch out the GC implementation as the code producer. You don't have to worry about what it is. I would argue when you do real time and you don't know that it's a reference counting GC, that might actually be a bit of a headache, right? Because it can cause a lot of pauses if you don't know about it. And
I completely agree with you, and that's why I didn't say it. That's why I didn't say it. But no, I think that is actually a real issue, because I think for people who are using WebAssembly, you are going to compile some module and think that you're fine. You're going to think, oh, I can run this in any runtime and it's okay, but that's not going to be the case. Your runtime is really going to matter, and the type of GC algorithm is going to matter a lot. So I'm hoping we get things like some kinds of hints or things that we can have that say, hey, actually, I do need a real-time algorithm for this, or I don't care, just do whatever you like for this. But I do think that is going to be an issue, but I don't think it's going to be that much of an issue. I think for people who truly care about real-time or other things like that, they're going to know, I'm just going to run the specific runtime that has this algorithm. I think for people, 99% of developers, it's not really going to matter.
Yeah, I mean, especially since if you know your ecosystem, you can make certain assumptions, right? Like on the web, you usually have, I guess, incremental collectors. So.
Yeah.
Anyway, okay.
Yeah. All right. Thank you very much, folks.